Can I just get a quick confirmation that you can hear me? Can someone just type in the chat and say yes? I can hear you. Oh, thank you. So let's get started today. This lecture will be recorded and posted onto Moodle. I hope everyone had a nice reading week. In the past lectures, I did mention that there are ways to evaluate whether your ground improvement was successful. You can probably imagine it is quite difficult to check whether ground improvement was successful for a very large plot of land. So we can achieve this by carrying out what we call in situ testing. And that's what you see here with this word here, in situ testing to evaluate ground improvement. Before we continue in our course to discuss other forms of ground improvement, I want to give you a bit of background on the method of evaluation first. So we'll take a quick detour in our lecture just to talk about two of the most commonly used evaluation methods, particularly in Hong Kong. And of course, we will cover the SPT method and the CPT method. The former is for more granular type materials, and the latter is for soft soils predominantly. So as I mentioned, we do need to sometimes check whether ground improvement was successful. As you'll see later on, when we discuss some chemical means or replacement means of ground improvements, we need to be able to quickly tell our client whether the strength and stiffness of the ground has been increased. So we mostly rely on in situ testing for this. What is in situ testing? Well, for a very large plot of land, it's very difficult to obtain samples that are representative of this large piece of land. Also, if you have very soft clays, it's not so easy to get samples and transport them back to the lab. For example, if you have undrained shear strengths of maybe 5 kPa initially, it's hard for you to get a strength profile in the ground, or strength with depth, essentially. So we want to obtain an indication of what the initial or in situ strength is and compare it with what happens after we carry out ground improvement. So soft soils is definitely an occasion where we would adopt in situ testing. Stony soils are also difficult to characterize in terms of strength and stiffness, because you can imagine when you try to take samples, very granular soils will just disintegrate. And these very coarse grained soils are mostly, I guess, supported based on granular contact, right? So it's difficult to sample very large stones and bring them back to the lab for testing. Most of the lab equipment can't really accommodate large diameter particles anyways. So that's another instance where sampling is difficult. You can imagine that in normal soil conditions, what we can do is, if we have a plot of land here, we can send a team of people to essentially drill into the hole, drill a borehole, and then we can lower some device into the hole and extract the soil sample. So we can take the soil sample here, bring it to the lab. We can do a triaxial test, odometer test, or whatever we need. But this is probably not that efficient. You can imagine in some cases, what we have to do is drill to a particular depth, take a sample, drill to another depth, take another sample, drill to another depth, take another sample. So if we wanted to obtain, let's say this is depth, and this is, let's say, undrained shear strength. If we wanted to obtain some continuous profile of the strength, let's say this is before ground improvement, and we want to see substantial increase in strength after. It's difficult to do it like this because you'll only get some points that you need to fit a curve through. So hopefully over the course of this lecture today, I can explain to you how we evaluate ground improvement. And likewise, it's difficult for sand and gravel to be transported in terms of intact samples. What I mean by intact is that when you extract the sample from the ground, they remain coherent enough for testing. Clay with high cohesive properties can be transported, cut, and placed in a triaxial specimen odometer test. But you can imagine that granular materials, as you remove, will just collapse to the angle of repose. Likewise, it's not easy to break off relatively strong fractured rock material and bring it to the lab. Now, in terms of in situ testing, there are two main ways to do it. In situ means we leave everything in the ground and we try not to remove anything as we do in conventional soil testing. The first means is by mechanical means. And we'll be looking at two main methods today, particularly CPT, which is the cone penetration test. And SPT is the standard penetration test. So we'll rely on these two means here. And the second part here, geophysical, essentially means, well, it's not mechanical, it's a non-invasive means where you send some sort of wave. It can be compression waves, shear waves into the ground. It could be acoustic waves, sound waves. And when you send these waves in the ground, they reflect and return back to you. And based on the time, length, and velocity of these waves, you can correlate it with the stiffness of soil. You can also use geophysical means to detect large voids in the ground. Now, in particular regions in Hong Kong, there are karstic formations where there are large voids in the ground. And of course, we're worried that our bore piles, for example, might end up sitting on a large void. And this could be problematic because we impose very high loads on our bore piles when we build, let's say, superstructures, right? So geophysical means could be a quick, easy way to scan the ground to identify potential voids before constructing bore piles, right? So for the most part, I think geophysical means is quite advanced. So we'll just focus on mechanical means, particularly CPT and SPT, because these are predominantly used in industry. Now, in terms of mechanical means, there are by all means other methods besides SPT and CPT, as you can see on this slide. And SPT, as I mentioned, is our standard penetration test, and you'll see very soon why we call it standard. And cone penetration test is CPT. When you're doing your capstone project, you're probably looking at borehole logs. Some of the borehole logs may have additional information about SPT and CPT properties. For SPT, you might see N values, right? Or we call this flow count. So we'll talk about what this is later on. CPT, if you're working with soft soils, you will probably proctor some CPT tests, right? So this is mostly for soft soils. Both of these methods require a reliance on penetration. This method here, this is a hammer, and we'll talk about this in more detail in a bit. And we would characterize SPT tests as some sort of dynamic penetration, whereas this would be probably a hydraulic, static pushing into the ground. So they're both in terms of penetration. That's why you see the word penetration, except one is done dynamically and the other is through static means. You see three other methods here. We have a flat plate dilatometer. These are less commonly used in Hong Kong. They're used globally, but we won't talk about these too much because it's not possible to cover all of these methods within the scope of this course. But I think it's quite imperative that we do understand the basics of SPT and CPT. Both the flat plate dilatometer test, DMT, and the freeboard pressure meter tests rely on inserting some probe to a particular target depth of interest. And there's some plate here and mechanism here that can expand, and you can get stiffness and compressibility of the ground. Likewise, for the pressurometer, you can pre-bore to a particular depth before you lower this PMT in the ground. You can push in a PMT as well. You can also have the newer form of PMTs that can self-bore down to the elevation of your choice. And once you reach the elevation, what a pressurometer does is it relies on cavity expansion theory to expand in various directions so you can get stiffness parameters of the ground. And if the material is weak enough, such as soil or weak rock, you can also get the strength of the material. If you've played around in a soil lab, you see this last method here is vane shear test. The vane shear test also has handheld devices. Essentially what a vane shear test is, you have a cruciform, so it looks like a cross, right? Crucifix from cruciform, right? With 4 veins here, you push to the ground and you apply some sort of moment or torque to this device. And what happens is when you apply some sort of rotation, the cruciform will break off, well, supposedly break off into some cylindrical soil here. And by breaking off, by knowing the moments, we can deduce the strength of the material. So the VST can give you the undrained shear strength of a particular soil. So this is just a quick summary of the most common used approaches in ground improvement to evaluate whether the strength of the ground, stiffness of the ground has improved. And as we mentioned, we will look at SPT and CBT mainly because they're used quite commonly in Hong Kong. All of the methods that you see on this slide are biomechanical means instead of geophysical. Geophysical would be we send weights, as I mentioned. And I talked about how each of these rely on some sort of torque, expansion for these two cases, for DMT, PMT, and penetration for SPT and CBT. There are different ways to interpret mechanical in situ test data. One way is empirical. Why is it empirical? Well, it's very difficult, as you'll see later on in this lecture, to come up with some mathematics or theory that can describe the complex mechanics of a hammer dynamically impacting a hollow split spoon to jam into soil in the ground. Now, this process is so complicated, even if you tried to characterize it mechanically, there would be lots of empirical fitting coefficients because we simply do not have the physics that can comprehensively and robustly capture the mechanics involved in, let's say, SPT tests. So we rely on something very empirical, like as you see in your capstone reports, we often see blow count N, and we have no choice but to relate this to strength and stiffness parameters, right? Or we can relate to soil type. Let's say we have phi. Let's say you have Young's modulus, for example. So we can relate the blow count to this, and we'll talk about blow count later on. Other means of what we talk about when we are other reasons for empiricism is we can't really map out stress paths because dynamic loading for SPT testing, for example, is very difficult to draw the stress path because we don't really understand positive behavior of the soil. We also cannot control the drainage conditions like we can, if you imagine for a traxial test, we can control the applied stresses for a traxial test in the vertical direction, the radial direction. We can also control whether we have drainage in or out of the specimen, and this allows us to map very detailed stress paths, let's say in the QP space, right, P prime space. But for empirical methods such as SPT, it's very difficult to draw these stress paths, analytically, that is, right? So this is what we refer to as empirical interpretations of mechanical in situ test data. If we want to become more elegant in our interpretation, then we can progress towards semi-empirical methods from empirical methods. Now, semi-empirical methods mostly rely on, for example, some theory and some well-founded principles. So we can actually solidify some relationships between measurements in the field and parameters with clear physical meaning. So these are parameters with clear physical meaning. But the story is nevertheless not complete, so that's why we call it semi-empirical. There are still elements of procedures that we don't understand. So an example is vein shear test, right? I showed you a cruciform earlier. So although it seems quite straightforward that, look, we assume that the soil fails as a perfect cylinder around this cruciform, well, then the question we have to ask ourselves is, yes, but under what assumptions have we made by assuming that this fails as a perfect cruciform, right? Well, for the VST test, which we won't talk about, so this is VST, vein shear test, we've made several assumptions. We assume that the process of penetration into the ground, this is the ground, we actually lower the cruciform into the ground. We assume that this penetration process doesn't cause any disturbance. We assume it doesn't cause any effective stress or shear distortion, which is highly unlikely. We assume that there's no drainage before and during shearing. This is, of course, an idealization, but not a bad one. We assume that soil is isotropic and homogeneous. We assume that the failure mechanism is cylindrical, which may not be the case. We assume that the diameter of the shear surface will be equal to the width of the vein blades. We also assume that at peak and remotest strengths, there's a very uniform stress distribution. We also assume that there's no progressive failure, so that maximum torque is your entry shear strength. So this is just an example that, for example, even the vein shear test I just talked about has a multitude of assumptions. So that's why we rely on semi-empiricism, and we have to apply different types of corrections to correct for the idealizations we make. Otherwise, our theoretical estimates of the shear strength for VST would be too high. So that's what we refer to when we say semi-empirical. And that's what we mentioned here. There are numerous assumptions here that make the process semi-empirical. Moving on, the next method of interpretation is analytical. There are methods that are purely analytical and rely very little on empiricism. For example, pressurometer is based on well-defined cavity expansion theory. Of course, we're not going to talk about this, but we're probably going to focus predominantly on the empirical interpretation. But I do want to let you know that there are more elegant methods of in situ measurements that rely more on theory and are more elegant, right? In pressurometer tests, we can actually draw stress paths because if you remember, the pressurometer is we lower something inside the ground, and we have some sort of membrane here, and we expand the membrane, right? When we expand the membrane, we know the volume, and we know the stress inside this section here. So we know the stress strain behavior, right? If we know the stress strain behavior, it can very much be analytical. So these are just different ways of interpreting in situ data. As I stressed again, we will be focusing on SPT and CPT, which I find mostly empirical, but still common knowledge that a geotechnical engineer should know about. There are different types of mechanical tests, as you've probably seen in the schematic I showed you about 2 slides ago. We can look at penetration. Penetration resistance can come in, as I mentioned, static or dynamic. Strength and compressibility. So these are SPT, CPT. Strength and compressibility, we won't look at so much, but dilatometer, we have pressure meter. In situ permeability can be determined indirectly from CPT testing. So, but most of the time, we have to simplify in situ permeability and assume undrained process to get undrained strength, right? So you'll see this later on. Now, if we want to talk about permeability, let's discuss drainage conditions during in situ testing. When we talk about SPT and CPT, you'll realize that we can virtually not control drainage conditions. If you remember from earlier lectures, I talked about how drainage is more or less dictated by the permeability of the soil involved and the rate of loading. So when we do these types of tests, we cannot guarantee whether we have an idealized drained or idealized undrained condition. Now, this in reality is probably somewhere in between a perfectly drained and perfectly undrained condition. Okay, so we have to make some assumptions here if you want to interpret the data for these different types of in situ methods. So that's the first thing I want to talk about. The second thing is we often can assume drain conditions only if we carry out the rate of penetration, for example, or loading at a very slow loading rate. And this rate of loading would be so slow that it would be not pragmatic in the field. And it'd be extremely costly to have a rig moving millimeters, right? In penetration depth, let's say in an hour, right? We can't afford that. So it's not practical. So we do have to make some assumptions here of whether it's drained or undrained. And we have to forego the conclusion that, yeah, it's probably somewhere in between in reality. That's the second point. Now, if we carry out tests in clay, it's unlikely that we can get drain conditions anyways. So we might as well just assume a drain and carry out these tests with rapid loading. And the more rapid we apply the loading, based on very low permeability clay, we might as well assume that it's a drain, right? Of course, then again, this is not something you can corroborate with any certainty, because even in MD material in Hong Kong, even you're not going to get a homogeneous MD material. You're going to get silts and clay lenses here, right? So when you try to do a CPT test through here, you'll probably get some, let's say this is silts or sand. You might hit some of these silt or sand lens, right? And then you'll notice different pressure responses. We'll talk about this later on. Yeah, anyhow, I just want to stress on this slide that we have to make very bold assumptions here on the drainage condition. And if we understand anything from soil element testing, drainage conditions dictate the mechanical response and interpretation that we deal with in soil mechanics. So anyways, if we assume undrained, we'll deal with undrained shear strength. And If you work in very pervious soil, very pervious gravel or sand, then perhaps you can deal with effective stress parameters like C dash and phi dash. So this is just a summary of the basic principles and the bold assumptions made regarding the drainage conditions and permeability of the soil. So this somehow provides a summary of what we will talk about today. What I've shown you in the schematic with the 5 different approaches, SPT, CPT, DMT, PMT, and DST, in the 3rd slide of today's lecture, still doesn't cover all of the in situ tests that there are. Barely scratches the surface if you look at this table, but let's only look at the most commonly used ones. So we look at SPT and CPT. You can probably look at this table. You can see a Marchenti dilatometer, as we talked about. We have pressurometer, plate loading tests. For those of you that have worked in the field, you've probably seen some of this. We have vane tests. Then you have geophysics tests. You have different types of pressurometer. These are in situ permeability tests. We can also measure the in situ permeability of the ground using falling head test, constant head test, Packer test. Of course, Packer head test would be in rock, right? And this table essentially summarizes what you can obtain in terms of parameters, right? We have at rest breath pressure, phi dash, undrained shear strength, confining stress, stiffness parameters, and last but not least, bulk modulus. So these are stiffness parameters, and these are strength parameters. I guess this would be a unconfined related method for cohesive soils, clay, for example. Some are also suitable for rock. And you can see on this table here that SPT is actually quite versatile, right? You can get phi dash correlation empirically for granular soil. You can get undrained shear strength. You can get the strength of rock, and you can get the various stiffness parameters for gravel, rock, and clay. CPT, we normally don't use it for gravel, as I'll explain later on why. It's usually mostly used for soft soils, and in some instances you can work with gravel material, but mostly it's for clays, and you can get stiffness parameters as well, but mostly for undrained shear strength. That's what we use CPT for. So this is just a summary of all the different methods and the parameters that we would be interested in. Now, let's go back to the topic at hand today. I just want to give you some overview of the other types of in situ tests, so we don't think that there are only SPT and CPT in this world, right? There are a multitude of other methods as well. Now, as I mentioned, for penetration testing, there's dynamic and static penetration. For dynamic penetration, we drop a hammer and we call it blows. We use the self-weight of the hammer to impose a dynamic impulse onto an anvil, and the anvil will push some sort of split spoon sampler into the ground, as you'll see later on. In contrast, static loading requires a hydraulic push into the ground, and that's what CPT is. So before we jump into SPT, I want to show you a quick video of what SPT looks like. So with SPT, you cannot get this profile. What you need to do is you need to rebore. You need to drill a borehole to your target depth. So what you see right now is an auger. Auger is drilling to a particular depth. It's drilling, and once it reaches the depth, they'll reverse rotation. So the auger's coming off the ground right now, and they've reached the target depth that they're interested in. Once this happens, you can switch in or replace the auger with a split spoon sampler. And we'll talk about what the split spoon sampler is in a bit, but I want to watch this video first because it helps a lot to look at something in the field rather than to jump the gun. So, sorry, the auger's still going to the target depth, still trying to reach the depth that they're interested in, sampling the strength of stiffness, right? So let's speed up a bit. Oh, I think that's too much. Okay, so they reached the target depth. Now, for this device, the split spoon sampler is already in the closet. The split spoon sampler is inside the auger. And now they're going to replace the mechanism to allow SPT test. So extraction is going on. And they put the sampler back into the ground. And now they put hammering devices, an automatic device. It'll be much clearer when we look at the theory. So a split spoon sampler is what samples soil out to good depth. And now they will apply different types of dynamic flows, and they have to measure how much penetration there is in the ground. That's why they have to mark the rods first. I'll post these videos onto Moodle, so you can take a look at your own time again. So the hammer is automatic in this case, and it's going in. It's hitting an anvil. At the top, there's a hammer, and it's penetrating this rod in the ground. At the end of the rod is a split spoon sampler. And these workers here are essentially counting the number of blows and measuring the penetration. And I'll talk about how we measure the penetration, what it means when we stop, when we terminate later on. So the split spoon sampler is being pushed in the ground by dynamic penetration. At the top here, there's a hammer that's automatic impacting split spoon. We can come back to this video after I give you a bit more theory, but after they're done hammering or they reach a termination criteria, which we'll talk about in a bit, they can remove the sampler from this borehole. The auger here is a hollow auger, so you can change different types of tools in the middle of the auger. So now they're removing the rod from the middle of the hollow auger. And at the end is their split spoon sampler. So then they can take the split spoon sampler off, and they can open the split spoon sampler before we were using as advertisements. So let's talk about some of the theory first. So for standard penetration tests, what happens? We have something called a split spoon sampler, or a split barrel sampler. Why do we call it that? Well, if you look at this, we can actually open this up in two halves. You can imagine you can connect these together and they'll form a nice cylinder, right? But you can pull it apart and you'll get something called a split spoon. We split the spoon essentially. And what happens with a split barrel is it's actually hollow on this end. And when you try to push it into the ground, the soil will move in and fill up your sampler. So that's why we call it a split spoon sampler. And SPT is interesting in that you can also collect soil samples. However, the soil samples are highly preserved, meaning that they're not very useful for, let's say you want to use a specimen for intact traxial tests, intact odometry tests. You can only use the soil that you get in the split spoon sampler for very coarse observations, such as PSD, water content, or soil description. So because the soil is highly disturbed from dynamic penetration. Anyway, so that's a split spoon, and typical split spoon or split barrel samplers are standard in size, right? So if you look at the dimensions here, you can see that the outer diameter and inner diameter is 50 and 35 millimeters respectively, and the length is 760 millimeters. So this is standard. That's why we call it standard penetration test. The split spoon or split barrel we use will have the same dimensions. Often there's also a device that allows air to escape. There's a bearing perhaps, or some sort of valve to allow a ball valve to allow air to escape. You can imagine if air doesn't escape, it's hard to get the soil into the split spoon sampler. So this is the standard penetration test. And what's essentially happening is you have an anvil here that's fixed to the rod, and you have some hammer that's standard as well, 63.5 kilograms to be exact, falling a height of 0.46 meters each time. And each time it falls and hits the anvil, it will push this sampler deeper and deeper into the ground. And this is the elevation that we're initially interested in the ground. And you can see from the video that I showed you, we often bore to the elevation we're interested in using an auger. In the video, what happened was the hole was supported by the auger. So we used an auger, right, to drill into the ground to reach our target elevation. But in the video I showed you, we had something called a hollow auger. So the auger is used to support this borehole so it doesn't collapse in that case. Anyhow, but let's assume that the borehole is competent, doesn't collapse. And what we do in an SPT test is we can keep on hitting the anvil until we reach some target penetration depths. Now, since this is a standard test, there are, of course, standard procedures to follow. There are three main stages that we need to consider in a standard penetration test. The first stage we call seating rounds. Now, in the seating rounds, what we care mostly about is to let the sampler just sit snugly on the surface. And why do we have a seating round? Well, normally when we're boring, this soil here becomes highly disturbed from the augering process or the mixing and the drilling process, remolded, right? So we don't really want to test this part of the soil with SPT test. So we have a seating round to try to get the split spoon a bit deeper in first, to be precise, about 150 millimeters deep, before we carry out what we call the first and second increments of the test drive, right? So the seating round is also something we record, as I'll explain later on. So the first stage is the seating drive, as you can see here. And when you're doing your capstone project and you see N values, number of blows, it's for a distance of 300 millimeters. And the seating round is 150 millimeters. And there are also cutoff values. For example, in most cases of Hong Kong, the cutoff value is 50. What do I mean by that? Well, if it takes 50 counts, 50 blows with the hammer, and you still cannot reach 150, then you stop, right? There's terminating criteria. For example, there's also for the actual testing drive, if you exceed 100 counts and you still can't get 300 millimeters, then you stop, right? Otherwise, you're going to damage your equipment. Or we just assume that the ground is firm enough that we don't need to keep on hammering it. Now, I'll talk about later on how these N values vary from project to project in Hong Kong, and it can be quite confusing. So anyways, there are two main drives. We have the seating drive and the testing drive. We take blow count measurements every 75 millimeters. So for 150 millimeters here, this is 150, right? We take two measurements. We count the number of N per 75. And for 300 here, you have that you read. When we look at how SPT data is counted in the next slides, you'll understand more clearly what I mean by 75 millimeter increments. So this is the general logistics of an SPT test. So the first step, if we look at this procedure, is to lower your sampler to the bottom of the borehole, which is what you see here. The next step is to see if the self-weight of this entire device will cause any penetration, right? If the self-weight of this exceeds the 150 plus the 300, so this is 450, right? If the self-weight is enough to penetrate this depth, then you just record it and you say the N is 0. It means your soil is very soft and very weak. But anyways, that's not often the case. So after you do the initial penetration by the self-weight, let's say it doesn't do anything, and the sampler just sits on the surface, then you carry out your seating drive. When you carry out your seating drive, you're essentially measuring the number of blows the drive hammer requires to achieve 75 millimeters of penetration until 150 millimeters, okay? If the penetration of 150 millimeters cannot be achieved because the ground is so stiff, then you just record the number of blows. And depending on which project, there could be a termination criteria, let's say. As I mentioned, if N equals 50, then you stop automatically. But let's say after N equals 50, you cannot reach 150 millimeters, then you stop anyways. So after the seating rounds, let's say we get here and you get your 150 millimeters, okay? And the next part of the process is to do the actual SPT test. So second and third stages of this would be what we call the testing drive. This is the seating drive. So for the testing drive, the number of blows the drive hammer requires to achieve 75 millimeters each time. So 150, so 75, 75. So we take 4 readings and we count the number of N it takes to reach here, the number of N's it takes here, and the number of blow counts for each 75 millimeters. So 75 times 3, 4, and then you get 300 millimeters, right? So we do that essentially. And let's say everything goes smoothly and you get your two 150 millimeter increments and you count the number of N's, then you stop. And again, for the testing drive, there are also termination criteria. Let's say it's 100. If you smash the testing drive more than 100 times and you can't reach 300 millimeters, then some projects would advise you to just stop. So after you reach this founding level here, and let's say you achieve 300 millimeters, Then the next step is to remove the rod, remove the sample trapped inside the split spoon. So notice how initially the split spoon is empty here, right? And as we push in the split spoon, the soil fills up the split spoon, right? So eventually, the last stage is to remove the sampler from the grounds, open the split spoon, and look at what soil is inside. So after we remove this, we can, as I tried to show you earlier, there would be, you can open up the split spoon into its two halves. And what you would see is there would be soil inside here, different types of soil. And you can look at the soil, you can take a sample of the soil to get the TSD, you can take the soil to get the moisture contents, but probably nothing more than that in terms of testing. So this is the overview of the SPT test. And bear in mind that everything is standardized. That's why it's a standard penetration test, including the height of the hammer and the fall height. The fall height is, I think, about 30 inches, equivalent to 0.76 meters. So this is how SPT test looks like as an overview. Now, for a standard penetration test, for most tests, it requires that we drop the hammer at a rate so that we achieve about, let's say, 20 to 40 blows per minute. So that's the general rate that we want to do. And we also want to make sure that the side of this borehole is stable, right? We don't want soil to be collapsing during the test as well. So we tried to maintain the borehole. And as you see in the video earlier, you can use a hollow auger or casing to maintain the borehole. But we should not extend the casing beyond our testing elevation, right? Otherwise, it would highly disturb the soil underneath. And if we want to obtain flow counts, we don't want to disturb the soil because it will affect the results. Some other things I do want to mention for the split spoon sampler, if we close it again, looks like this. We can also have what we call the core catcher. So core catcher allows anything to come in, but it doesn't allow anything to fall back out. So core catcher is good for catching finer material. Maybe we can catch some sand so that when you open the split spoon, you can actually see all types of soil. If you can't catch the material, then it might just fall out of the sampler. So let's talk about some key points of SPT test, because I mentioned a lot of information just now. The first is that the SPT test is mostly used for cohesionless soils, granular materials, to collect disturbed samples. Now, what do I mean by disturbed? You're unlikely to be able to use this as intact triaxial specimen or odometer specimen. And you can only really get PSD, particle size distribution, water content. You can also look at the texture of the soil and describe it. That's about it. That's what we mean by disturbed samples. You can use the N value that you get, flow count, and relate it to the in situ strength. In Hong Kong, we're very rich in SPT data, so we have lots of correlation to get very good strength correlations. And in Hong Kong, we have so much data, in fact, that we can get very reliable internal friction angles for local cohesionless soils. For cohesive soils like clay, we still can actually get decent in situ undrained strength parameters as well. And I mentioned that this test is a standard test, so we typically have a 63.5 kg hammer or 140 pounds, dropping 30 inches or 0.76 meters to blow the anvil each time. That's how much energy is applied to the hammer. And we'll talk about later how this can sometimes cause a lot of discrepancies because there's a lot of energy loss in the process as well. And I think our time is up today. So we'll carry on in the next lecture. And I'll see you on Friday then. Yeah, see you then.